Welcome to this presentation. I'm Benoit from the University of Oxford, and I'm going to talk to you about the climate datasets that are being generated within the MaRIUS project. So I try to give you an overview of what is being done within MaRIUS. You're probably familiar with the MaRIUS project to some extent. What I'm going to talk to you about is the hydrometeorological drought event set that is being generated by the climate team, and that will then be fed into various hydrological and impact models to assess the risks of water scarcity. So the drought event sets, the idea of the drought event sets comes from the realization of the fact that extreme events, including droughts, are rare by definition. So we only have a few observed events in the observational record, while we would need a larger sample to be able to quantify the risk. So in addition, an event is basically can be split into two parts. On the one hand, the meteorological hazards, so for example low precipitation or high evaporation, high temperatures that lead to a drought, which and then these meteorological conditions lead to impacts. So the drought event sets that we're producing basically consist of spatio-temporally consistent sequences of weather for thousands of synthetic, meaning potential, drought events. So if we think about the MaRIUS climate products, the drought event sets basically are possible, or is a set of possible time series of the weather that could have occurred in the past or could occur in the future as a result of the various factors that influence the climate, such as greenhouse gases, sea surface temperatures, volcanoes, etc. This is different from the observed time series that we have in the past, which actually occurred, but that exactly this time series occurred is by chance. And conceptually what happened is one of many possible time series that could have happened, and equally likely. So the drought event set aims at spanning all the possible time series that we might have experienced or that we might experience in the future. What we're producing is basically 100 time series for each of 3 time periods. First, a recent past, which is slightly more than a century, 1900 to 2006, and then 2 future time slices of 30 years each, near and far future, as shown here. In addition to this drought event set, we also create a product called the Hindcast here, which goes back to 1851 and extends until 2014. And this is basically a dynamical downscaling from a reanalysis. So this actually is a representation of the time series that's actually occurred in the past. And I'm going to start with the Hindcast. Very briefly, what it's doing is using the regional climate model HADARAM3P from the Met Office, and using the 20th century reanalysis as a boundary condition. It is basically dynamically downscaling the weather to 25 by 25 kilometers grid cells. So the 20th century reanalysis is a product that's basically based on a model which assimilates observations, but in that case, to go that far back, only surface pressure observations and the oceans are considered. So there are some biases, and in particular relevant here, well, the UK, we get a warm, dry bias in summer. Nonetheless, this is useful, and the role of the Hindcast in MaRIUS is really to put the event sets in the historical context and go far enough back in time for that. The drought event set, on the other hand, is using Weather at Home. So Weather at Home is part of the climateprediction.net project. what we're doing within this project is basically we're using computing time from volunteers around the world to run our climate models, which allows us to run very large ensembles in the order of thousands or tens of thousands of climate model simulations. So the setup consists of a global climate model, Adam3P, at roughly 150 kilometers, and then over sub-regions such as Europe here, a regional climate model, Hadaram3P, which is the same that was used in the Hindcast as well, typically at 50 or 25 kilometers. And then the models are forced with observed sea surface temperatures and sea ice, greenhouse gases, etc. And this setup allows us to generate really multiple sequences of weather that could have occurred under this forcing. So really what we're doing in that case is sampling the chaotic variability of the atmosphere and looking at a whole range of possible time series that could have occurred or could occur in the future. For MaRIUS, we've done a few improvements to the model. For example, we've increased the resolution of the regional climate model down to 25 kilometers. We've implemented a new land surface scheme, MOSES2, which uses styles to better represent land surface heterogeneity within grid cells. And in terms of the forcing that's used to drive the model, we are using the new sea surface temperatures and sea ice dataset HADIS2. And for the future, we're using a synthetic dataset created by Neil Massey in our group, which basically uses CIMI5, so the coupled climate models, to estimate long-term trends in sea surface temperatures and sea ice, and apply these to observations. And then internal variability and the seasonal cycles are derived from the observed. So how do we then build our drought event sets with this setup? Basically, with weather at home, we run about 100 runs per year for each of the year within our 3 time slices. It should be noted that the future time slices are 30 years periods that are based on 1975 to 2004. This means that actually the sea surface temperatures are taken from these years as a reference, and the warming from CIMI5 is added to those. We then output relevant daily and monthly variables, so things of course relevant to droughts, such as daily minimum and maximum temperature, precipitation, and variables needed to compute potential evaporation. And we then identify droughts within these time series using SPEI at various time scales. I'm not gonna go into details on this today. And in overall, if you think about each 30 years periods, we have 100 simulations. This means that we get about 3,000 years of data with lots of drought events in there to be analyzed. Now, these were using, or in these simulations using weather at home, we get always single years simulations. How do we go from there to continuous time series? What we did for that, we considered the slowly varying components of the climate system, which have memory and may impact the weather. Of course, an important component is the ocean, but the ocean in these experiments are prescribed to the observed, so by definition they're continuous when you go from one year to the next. And another variable which exhibits memory and may impact the weather is soil moisture. And soil moisture has another very nice property, is that it is basically an integrator in time of precipitation minus evapotranspiration. So by making sure that when we are looking at our single years to put them together, when we make sure that soil moisture is continuous, we ensure also that the history of the weather is similar as well. So basically, our approach is to stitch, if you like, yearly simulations using 5 days soil moisture averages. Just to give a small illustration, this is just an example with kind of random data. What you see here are our simulations for 3 years, or some fake simulations, and this is, you see time series of soil moisture for different simulations, 1981, 82 and 83 in colors, and you see that each of these simulations have a previous year that has been run, a spin-up run, which is shown in gray here. And what we're trying to do when finding out which run in 1981 should be stitched to which run in 1982, we're trying to match the soil moisture. And to do so, we use the end of the year, so the last 5 days averages soil moisture in December 81 to that we compare to the to the same time step in the spin-up simulations of the simulations 1982. So we're matching the same time steps. Of course, in our case, we don't have just one time series, but we have spatial patterns. So we use empirical orthogonal functions to simplify our multi-dimensional fields, and these are the EOFs of the upper measure soil moisture for the last pentad in December. You see that the first pattern on the top left here explains about 43% of the variance, and it is homogeneous in sign, meaning that basically it tells us, this first EOF tells us whether the UK was dry or wet. The second EOF explains 16% and tells us something about the southeast-northwest contrast in soil moisture. And then the third, fourth EOF explain much less of the variability. So we decided to retain the two first EOFs, and by plotting our last December values in that two-dimensional space, we find out which simulation are closest to the next year's spin-up simulations, and thereby decide how to stitch these runs together. We also looked at what or how well we can do it, and here what you see is the empirical cumulative distribution function of the distance in that space when we go from the last pentad in December to the first in January. So the black line is from continuous runs. You can see the distribution of the distance, so how much of a jump do we get from one pentad to the next. And then in red, what you see is when we do our stitching with the last December pentad with the last December pentad of the spin-up runs leading into the next years, you see that the distance is much smaller than that, and more interestingly, the blue line is then the distribution of the distances between the end of December of 1981, for example, and beginning of January 1982, when we stitch these runs using this methodology. So ideally, the blue line would line on the black line, and you can see that they're very close, so the error that we're making there is quite small. So that was a bit about the methodologies. Quickly about the performance of the model. So these are biases in mean seasonal surface air temperature for the 4 seasons, winter, spring, summer, and fall. And you can see that the biases are mostly within half a degree. So quite small biases. Slightly warmer in summer, but again mostly within a degree. So we're quite happy with that. In terms of precipitation, you see on the left here the biases in millimeter per day, and on the right in percent. It is overall the biases are not too large, but we get some biases, especially in summer and fall dry bias, that may have to be accounted for. In terms of the future projections, I show here on the left the changes in surface air temperature for the 4 seasons, from top winter to summer is the third row, and the left side is the near future, and the right side of the left plot is the far future. So you can see a warming for the far future. It's about 4 degrees in summer. And in terms of potential evaporation on the right, you can see large increases in summer especially. In terms of precipitation, what we see again on the left here are values in millimeter per day, and on the right these are percentages. You can see that precipitation tends to increase in winter by maybe 10 to 15% or maybe 0.2 millimeter per day, while in summer it strongly decreases. So we have really a drying in summer, about 40%. So yeah, and in spring and fall we get a slight drying over the land areas, but not as much as in summer. So I hope I've given you a small overview of the climate products that we're generating within MaRIUS. If you have questions, you're welcome to contact us, and thank you for your attention.